So now you guys are proficient in writing balanced chemical formulas, naming the resultant chemical molecule according to if it's an ionic, molecular, or acid. Now let's talk about how we can determine how much a compound weighs, also known as its formula mass. Now we've already talked about how to determine how much those beautiful things on the periodic table, aka the elements, we already know how to determine how much an element weighs. You look at the periodic table for that element and you use the atomic mass, that's the number underneath the name, and that's how much the element weighs in AMUs, or atomic mass units. So how can we use the periodic table and a balanced chemical formula to determine how much that molecule weighs? Well, for any compound, the atomic mass, or the formula mass, is the sum of the atomic masses of all the atoms in the chemical formula. That's why it's so important to be able to write proper balanced chemical formulas, because if your chemical formula is incorrect, then your resultant formula mass is going to be incorrect. So for example, NaCl, sodium chloride. I know I have one sodium for every one chlorine because sodium's a +1, chlorine's a -1. The mass, or how much one molecule of sodium chloride weighs, is the mass of one sodium atom plus the mass of one chlorine atom, both of which you get from the periodic table. In atomic mass units, you sum that up to get 58.44 atomic mass units. Similar dance when finding the formula mass for water, just making sure that you take care of number of particular atoms when calculating formula mass. So for example, in H2O, since there are 2 hydrogens, you need to take the mass of hydrogen and multiply it by 2, and then add to the mass for oxygen. So finding formula mass, done the same way regardless if you have an ionic compound or a molecular compound or an acid. You also would find formula mass for a compound given a monster like this, borax. I use this example in class for how to determine formula mass because for several reasons, one of which this molecule is a molecule that's called a hydrate. Molecules that are hydrates have water molecules associated with them. You are going to have a lab in about a week or so that is called hydrates. And so you're going to be dealing with or seeing molecules that look like this. Borax, I know it's a huge molecule. It's not one I would ask you to name, but I think it is a good representation of a hydrate and how to use the concept of formula mass to determine its weight. So to determine the mass, the formula mass of borax, you're going to do exactly what you did with the other 2 examples, just taking care to make sure you account for all the different atoms. So for sodium, there are 2 sodiums, so I take care of that here. I have 4 borons, 4 because of the subscript 4. Now oxygens. How many oxygens are in this molecule? And so we said that hydrates have water molecules associated with them. And we'll talk more about this in the hydrates lab, but that little dot in there just means that the water molecules are loosely associated with this part of the molecule. But you should be able to see this and say, oh, I've got 7 oxygens from this part, and from the 10 H2Os, I have 10 oxygens. So how many total oxygens do I have in this molecule of borax? I have 10 plus 7, or 17. So that's why when I find my formula mass for borax, for the oxygen part, I take the 17 and multiply it by, oh, I just saw that should be 16 AMUs. Sorry about that, guys. Professors make mistakes too. 17 times 16, though, is still 272. So my apologies. So I've got 17 oxygens and how many hydrogens? Well, that 10 goes to everything behind it. It went to the oxygen and it goes to the hydrogen. Remember, we multiply. So 10 times 2 gives me 20. So 20 hydrogens. So once I take the individual masses from my atoms and I sum them up, that gets me my formula mass for borax, which is 381.42 atomic mass units. So you should feel comfortable being able to find the atomic mass or formula mass for molecules as simple as water, but also as complex as this.